Let's design a parametric tower in BeeGraphy. Parametric design uses flexible parameters to shape geometry, allowing for easy adjustments and creative exploration. Create a parametric tower in BeeGraphy. Use arcs, arrays, and transformations to design a dynamic structure. Adjust parameters like diameter, height, floors, and rotation for endless variations, perfect for beginners in parametric modeling. Let's start with an arc that will form the main shape of each floor. This shape will serve as the foundation for building our tower. We use a diameter parameter for intuitive control of the tower's width, dividing it by 2 to calculate the arc's radius. The size parameter controls how far the arc extends around the circle, like adjusting the size of our cake slice. This directly influences the final shape of each floor. We'll divide by 2, as we will also use the opposite value. We'll convert the angle to radians using the deg to rad node. We also use the opposite node to reverse the direction of the arc, giving us control over the curve's orientation, which is important for the tower's spiral. We use a polar array to create multiple copies of our initial arc, arranging them around a central point, like the spokes of a wheel. This forms the radial sections of each floor. The endpoints node identifies the start and end points of each arc section, which are essential for connecting them. We use the shiftless node to rearrange the order of endpoints. This clever trick ensures that we connect the end of one arc to the beginning of the next, creating a continuous loop for each floor. The arc SD node connects the shifted and original endpoints, creating arcs that close the loop and define the floor's shape. A direction vector controls their curvature. The centroid node finds the center of each floor, and a direction vector from each centroid controls the curvature of the connecting arcs, giving the tower its outward curve. The join node combines the individual arcs of each floor level into a single, continuous curve. Now we have a complete outline for a single floor. We use the linear array node to duplicate and stack our floor outline vertically, building the total height of the tower. Now, we'll use the range input node to set the number of floors dynamically through an input, adjusting the tower's floor count as needed. We'll also define the height measurement using a parameter to control the tower's overall height dynamically. By dividing the height by the floor count, I calculate the spacing between each floor. A vector z is then created to instruct the linear array to stack the floors with the calculated spacing. Now, we'll use the curve-to-surface block to transform the stacked curves into surfaces. Now, we'll use the extrude surface tool to add thickness to the surfaces, turning each floor into a 3D object. Now, we will change the shape of the tower by rotating each floor around its center. We generate a list of angles, one for each floor, using the list sequence node. These angles will control the tower's spiral. We'll define the angle size using the range input node and name it rotate angle to control the rotation of each floor. We convert the rotation angles from degrees to radians for the rotate node and use the deg to rad node to make the conversion. The final touch involves enhancing the visual appeal of our spiral tube by applying material properties. The Apply Material node allows us to structure a realistic appearance by setting parameters such as color, metallicity, roughness, and opacity. Thanks for watching. We hope this tutorial helped. For more on computational design, please like this video, subscribe to our channel, and hit the bell icon to get the notifications. See you in the next tutorial.